Hi, welcome to my presentation on circular insecure encryption from long cycles to short cycles. This work was done while I was at the University of Victoria, and this is published in Communications in Cryptology, Volume 2, Issue 2. So this is a rundown of the presentation, and we will begin with the intro. So for an encryption function inc, a public key PK, and two different messages, generally the goal is for the encryption of M0 under PK and the encryption of M1 under PK to be hard to distinguish. And an encryption cycle, a length n encryption cycle involves using n keys pk0, sk0, all the way up to pkn-1, skn-1, and create a sequence of ciphertext where sk1 is encrypted under pk0, and so on and so on. So each public key encrypts the next secret key. And eventually you get to sk0 encrypted under pkn-1. And circular security is when we want the length n encryption cycles to be indistinguishable from a encryption of zeros. So instead of encrypting each secret key, we encrypt a zero string instead, and we want them to be indistinguishable. So why does this matter? Circular security can happen naturally, such as in Windows BitLocker, where a key used to encrypt a disk may be stored onto the disk. And there are other assumptions. And along with other assumptions, circular security can create very useful primitives, such as fully homomorphic encryption and indistinguishability obfuscation. Similarly, circular insecurity can also be used to create useful primitives such as witness encryption and lockable obfuscation. So what do we currently know about circular insecurity in CPA setting? With no concrete assumptions, there exists a folklore construction of one circular insecurity. So this works by given a pair of PK and SK, a public key and a secret key. When the public key recognizes that the secret key belongs to the same pair as itself, it will simply output the secret key without encrypting. And with concrete assumptions, there are many works, such as finding two circular insecurity, bit one circular insecurity, and there are works that finds circular insecurity for multiple lengths. Our results is that we constructively show if there exists an n+1 circular insecure CPA secure encryption scheme, then there exists a less or equal to n circular insecure but CPA secure encryption scheme. We use less or equal to n here to mean this scheme is one circular insecure, two circular insecure, all the way up to n circular insecure. Further, the constructed circular insecure scheme may preserve the message space of the original scheme. And with some modification, we actually have also shown that n+1 circular security implies n circular security. So we begin with public key encryption scheme. This is defined quite standardly. So a public key encryption scheme consists of three efficient functions: keygen function G, encryption function E, and decryption function D. For the simplicity of our work, we will just assume full correctness, which is given PK and SK, when we decrypt the ciphertext created of M encrypted under PK using SK, we can get M. But our results holds with other common correctness definitions, such as correctness, but only for all messages, but only overwhelmingly choices of the key pairs. Now we talk about what is CPA security, which stands for chosen plaintext attack. So a CPA security experiment is played between a encryption scheme pi and an adversary A. the experiment begins with first sampling PKSK using the keygen function and give data and the public key to A. A random coin B is flipped, and A outputs two equal length messages M0, M1. Then a ciphertext CB is computed from encrypting MB under PK, and this CB is related to A. When A outputs B prime, so the experiment results in 1 if A, the adversary A, can successfully guess B, and 0 otherwise. And its encryption scheme, it's CPA secure if for every probabilistic polynomial time adversary A, its probability of winning only has negligible advantage. And for circular security, we define an uncircular security experiment between an encryption scheme pi and an adversary A. So first of all, n key pairs are sampled from the keygen function. A random coin B is flipped. And then depending on the value of B, if B equals 1, an encryption cycle is created. A length n encryption cycle is created. And if B equals to 0, an encryption of zeros is created, and this gets sent to A. And the adversary has to guess B, and the experiment results in 1 if adversary A succeeds, and 0 otherwise. If an encryption scheme pi, we say encryption scheme pi is uncircular secure if for any PBT adversary A, its probability of winning in the experiment, in the uncircular experiment, has only negligible advantage. So the intuition for our result is that first we can observe an encryption scheme pi that is two circular insecure. This means that given length 2 encryption cycle, as we can see on the left hand side, SK1 encrypted under PK0, SK0 encrypted under PK1, this is distinguishable from an encryption of zeros, which is a zero string encrypted under PK0 and zero string encrypted under PK1. So if we consider a function f that takes two parameters, the first is a triplet phi0, phi1s. The second is psi, and it creates it outputs an encryption of psi under phi1 followed by s. We can observe that if for some encryption scheme where from encryption scheme where it has public key pk prime and secret key sk prime, where pk prime takes the form pk0, pk1, encryption of sk1 under pk0, and sk prime just equals to sk0, then when we compute f on pk prime and sk prime, this simply creates a length 2 encryption cycle of pi. So our idea is that we want for to create an encryption scheme pi prime from pi, such that for any cycle with length less or equal to n in pi prime, we can find a length n plus 1 cycle of pi. In the preprint of this paper, we also show that we can achieve uncircular security from n plus 1 circular security. So our construction is as follows. First, we let pi be a n plus 1 circular insecure but CPA secure encryption scheme. And then we construct pi prime with as follows. So the keygen function of pi prime is g prime. It calls g, which is the keygen function of the base scheme. We'll refer to this pi as the base scheme. It calls g n plus 1 times to get n plus 1 pairs of keys. That is pk0, sk0, all the way up to pkn and skn. And then it computes s, which is skn encrypted under pk0. Then for I larger or equal to 3 and less or equal to n, it creates hi, which is ski minus 1 encrypted under pki. Now it returns the public key pk0 up to pkn, followed by s, followed by hn, all the way down to h3. And the secret key contains SK0 all the way up to SKN-1. You may notice that SKN is never returned as part of the secret key, but it is encrypted in S, which is in the public key, and it is encrypted under PK0. The encryption function E prime takes PK and M and first parses PK into the components we described in the previous slide. And if M is not the length of a secret key, it will simply encrypt M under PK1 and output a tuple 0 followed by C. Otherwise, it parses M into the M parts similarly to a secret key, where each part equals to a small part of the secret key. And then it will encrypt MI under PKI plus 1 for I larger or equal to 0, less or equal to I minus 1. Then it returns a tuple where it starts with 1, followed by C0, all the way up to Cn minus 1, followed by S, where S was part of the public key. The decryption function takes a secret key SK and a ciphertext C. If ciphertext is a tuple of 0 followed by C prime, it would simply decrypt C prime with SK1. Otherwise, it first computes SKN from S, and then it returns, and then it decrypts each part of the C with the corresponding secret key, and then concatenate the result to reform the message. So now we show why this is circular insecure, and we began with an example by setting n to equal to 2. So the n plus 1 scheme would be a 3 circular insecure scheme. And we will show the pi prime constructed using pi is less or equal to 2 circular insecure. So for a key pair of pi prime, it would contain its public key has the form PK0, PK1, PK2 followed by S, and secret key has the form SK0, SK1, where PK and PKI and SKI is generated from the key gen of the base scheme, and S is generated from encrypting SK2 under PK0. So now we look at a length 1 encryption cycle of pi prime. So we have inc prime with parameters pk and sk. We can expand this out, and this will give us a tuple where it's 1, followed by encryption of sk0 under pk1, sk1 under pk2, followed by s. Now we can expand s, which gives us sk2 encrypted under pk0. And we can observe that this is a length 3 cycle of the base scheme pi, with the keys being pk0, sk0, pk1, sk1, and pk2, sk2. If we look at this figure here and we follow the arrow, we can observe pk0 encrypts sk2, and sk2's corresponding public key is pk2, which encrypts sk1, and the corresponding public key to sk1 is pk1, which encrypts sk0, which its corresponding public key is pk0. So this is a length 3 cycle of pi. Now for a length 2 encryption cycle of pi prime, we have sk1 encrypted under pk0 in E prime, and sk0 encrypted by sk1 using E prime. So this gives us the following ciphertext, and when we expand this out, this gives us the following. And again, we can find a length 3 encryption cycle of the base scheme pi. So we can observe that we found a length 3 encryption cycle with the keys pk10, sk10, pk01, sk01, and pk12 and sk12. So let's begin with pk10 here. We can notice that pk10 is used to encrypt sk12, and the corresponding public key to sk12 is pk12, which is used to encrypt sk01, and its corresponding public key is PK01, which encrypts SK10, which its corresponding public key is PK10. So this is the Lens3 encryption cycle of pi. You may notice that this is not the only Lens3 encryption cycle in this figure here. In fact, we can find another Lens3 encryption cycle. So if you follow the red arrows, this is the Lens3 encryption cycle we shown in the last slide. But if you follow the blue arrows, we can find a different Lens3 encryption cycles where each key is unique, where each key in the cycles are unique. So this blue cycle does not contain any key in the red cycle, and this red cycle does not contain any key in the blue cycle. So this means these are two independent Lens3 encryption cycles of pi. Following this idea in the appendix of the preprint version of this paper, we also show that how you can create uncircular security from N+1 circular security. Now we want to claim just generally that from N+1 circular insecure and CPS secure scheme pi, we can create a pi prime that's less or equal to uncircular insecure. We show this by having an adversary A prime L playing the length L circular encryption experiment against pi prime, such that this adversary can perfectly simulate the experiment of length N+1 circular game played between A and pi. So A prime L playing the L circular game would receive L keys PK0 up to PKL-1. And then it would parse each of the PK into PKX0, PK all the way up to PKXN, SX, HXN, all the way down to HX3. And then from these, it sends specific parts of these keys. It would send PKL-10 for I larger or equal to L+1, less or equal to N. It sends in descending order PKL-1I. And then following J larger or equal to 0, less or equal to L-1, it sends in ascending order PKL plus J-1 mod L, L minus J. And then it would also, once it receives the ciphertext, it would also parse it into the form that it expects. And then it sends the following parts from the ciphertext to A, which is L-1 and some values of H and some values of the ciphertext. What this does is that the encryptions here would perfectly simulate the encryptions of length N+1 encryption cycle of pi. So the public keys we carefully have chosen are used to create the ciphertext here, and each public key would be encrypting the next secret key. So yeah, so it can be simulated. So a length N+1 circular security experiment between A and pi can be simulated by the adversary A prime playing the L circular security game against pi prime. Now, to show CPS security of this scheme, we will use a sequence of games. So we're showing that if pi is CPS secure, then pi prime is CPS secure. Before we continue, I want to mention this uses the idea that when there are no cycles, an encryption scheme, when you see a bunch of ciphertexts but there are no cycles in them, it would be circular. It would be secure. So we began with game 0. This is just a CPA experiment, but we write out every step explicitly with respect to pi. So this CPA game is played between A prime and pi prime, But pi prime in each step, of course, calls to functions in pi. So first, the keys are generated, public key is sent to the adversary, random coin is a random coin is flipped, and then adversary chooses M0, M1. Depending on the coin, MB is encrypted and sent back to A prime. And A prime has to output B prime. So A prime has to guess the value of B and succeeds if B, and the experiment results in 1 if A prime succeeds and 0 otherwise. So in game 1, we can change how the keys are generated. So we sampled PK0, SK0 up to PKN and SKN similarly as before. But for S and the H values, we'll be encrypting zeros instead of the secret key. And now this is given back to the adversary. So the difference between this this experiment resulting in 1 and the previous experiment resulting in 1 is negligible, because by CPA security, we can replace these tags with zeros and for them to be indistinguishable, because if, with or without replacing these tags, there are no cycles created. So we let game 2.0 be game 1, and for j larger or 0, we define game 2.j. What this does is, in step 4 of the game, this is where after the adversary have sent in message M0 and M1, we change how the ciphertext is created before it gets sent back to A prime. So in game, say j equals to 1, right? So the first change we make is when we compute CBI, instead of encrypting the ith component of the message, we will encrypt 0 instead. And in 2, we replace n minus 2 and n minus 1 both with 0, and so on and so on. Until game n, we would have the entire message encrypted to be just 0. So in game n, this is what we have. Remember that we've replaced S and H with encryptions of zeros. And now, after the adversary A prime sends in M0 and M1, we if MB is not the length of the secret key, we just encrypt MB under PK1, and otherwise we will just encrypting 0 and sending this back to the adversary. So when the adversary sends in MB that's now equal to the length of a secret key, this is essentially exactly just a normal CPA game against pi. And otherwise, it's always receiving an encryption of zeros, which is independent of the value of B. So the advantage of A primes winning in game 2.n is negligible. And the difference between each game, so between game 0 and 1, and 1, which is also game 2.0, and the difference between 2.0 and 2.j and 2.j plus 1, they're all negligible. So in the end, we can claim that, we can conclude that the advantage of A prime in game 0 is also negligible. Now, in the paper, we have also shown that if the base scheme is a bit encryption scheme, the construction can also be a bit encryption scheme. And similarly for other message space. Also with minor modifications, we can show that we can also show that this result holds in the symmetric key setting. Now we will end this with some open problems. So in our work, we've only shown how to go from larger cycles to smaller cycles. And we think it would be very interesting to know if it's possible to go from smaller cycles to larger cycles in either uncircular security or circular insecurity. And this concludes the presentation.